Hello, and welcome to this episode of State Machine Corner. I'm Dr. Bruce Powell Douglas, Senior Principal Agile System Engineer at the Modern Corporation and Principal at A Priori Systems. In this episode, we're going to talk about pseudostates. Pseudostate is an unfortunate name in that they're neither pseudo nor states. What they are annotations of special semantics for state machines. In this slide, we see some of the most important pseudostates to be found in SysML and UML. So we have default and terminal, present in both Rhapsody and in Cameo Magic Draw. Junction, conditional, and choice points for conjoin. We won't talk about entry and exit points today. In the next episode, we will talk about submachines where entry and exit points are used, but they are pseudostates. We'll talk about history. We'll talk about the send actions. Even though they're not really pseudostates, they're actions, but we'll talk about them today. And we'll talk about the diagram connector, which is a Rhapsody-only feature. First of all, let's talk about default, terminal, and diagram connector pseudostates. These are really pretty easy. In general, every state context that has more than one state must identify the initial state. This is done with the initial pseudostate. Where do you start in the context? You can also have a terminal which terminates the state. Not always used. In fact, it's a little bit rare. Much more common in activity diagrams and state machines. And then we have a diagram connector, which provides a diagrammatic way of representing, drawing a transition in a diagram, where it's inconvenient to actually make the path from one state to the next state. In this diagram, we see those three features. Here we see the initial state. We start in exterior closed, interior closed state. That's the initial condition there. So when this classifier behavior is invoked, and we create the classifier, it enters into this state. We also have a terminal. So when this state is in chamber excised, it then terminates. We also see the diagram connector A. If you look at these two states, decontaminating and clearing, we would like to transition based on the doors opening, exterior doors opening, back to exterior doors open, interior doors closed state. But it's inconvenient to draw the transitions without line crossing and other things that would make the diagram messy. So in Rhapsody, you can have a diagram connector where they enter into a diagram connector with a particular name and exiting from the same name diagram connector to the target state. This allows us to have the path be defined but not have to actually draw through other paths to get there. Now let's talk about junctions, conditionals, and choice points. This is more interesting. Both Rhapsody and Cameo have some deviation from the standard here, and they implement the standards in slightly different ways. Let's look at the standard for junctions. These are ways of combining transition paths into compound paths. So there you can have guards and multiple exiting paths from a junction, and the guards are evaluated before that transition is taken. Before you decide to execute any actions whatsoever, the guards must be evaluated for correctness. This is different than a choice point. In a choice point, the guards are evaluated after the initial actions are taken and you get to the choice point. However, choice points come with a caveat highlighted in red here. If none of the guards evaluates the true, you end up in the choice point and your model is ill-formed. You can't move forward. Your model is just broken. For that reason, I recommend you should never use choice points, because there's a possibility you'll just crash your model. Let's see what this looks like. With Rhapsody, junctions are implemented in two different ways. First of all, there's the conditional. Conditional looks like this. Looks like a junction with a C in the center. Let's actually look at Rhapsody execute that. So here's Rhapsody. I can run this model, but here notice what we have. We have an initial action, x equals 0, so x is a value property set to the value 0. And then there's an exit action here, x equals x plus 1. This exit action is executed when you take a transition. There's a transition triggered by event E with the action x equals 5. Then there's the conditional state and two guards. In this path, x is greater than 0, and this is the else path. Let's run this and see which path it takes. Can you predict which path will be taken? Let's see. So we'll run the model, bring up our state machine, have it run. Now we will insert the event E, generate events, event E. It went to state 3, it took the else guard. But notice that the exit action was x equals x plus 1. So at the point when that action completes, x has the value 1. Then there's an action, x equals 5. So then it's overwritten with the value 5. So why did we take this path? We took this path because this is a static condition. Before any actions are executed, you must determine whether or not there's a valid exiting path. So the guards are evaluated. When the guards are evaluated, x has the value 0, because that's its value while it's resting in state 1. Therefore, x has the value 0, the else guard is true. This is the path that is taken. When you transition, by the time you arrive in state 3, the value of x will be 5. And in fact, if we look at the instance features, we see that x has the value 5 currently. So the reason why this path is taken is because the guards are evaluated first, and when the guards are evaluated, the value of x is 0. The other side of a junction is that for a junction you can have multiple exiting paths. However, in Rhapsody, this is what a junction looks like in Rhapsody. You cannot have multiple exiting paths. You can have multiple inputs, but only a single output. So if you try to do that in Rhapsody, you get this error message. Junction connector can only have a single outgoing transition. This is in conflict with the standard. It's not a terrible conflict because you have conditional to take the place, but it nevertheless is inconsistent with the standard. Let's see what Cameo does in the same case. So now let's go ahead and run Cameo. So here's the Cameo model, same model. But now, because the conditional pseudostate is just a Rhapsody thing, it just uses a junction, which is completely appropriate. Same actions, x is 0, and resting in state 1, the value of x is 0. And then there's an exit action, transition action, and we end up in one of these two states. The same thing should happen. Let's see what it does. So when we simulate this with context, we run it, we see we're in state 0, See here the value of x, a little hard to see I know on your screens. The value of x is set to 0. If I then insert this event, it goes to state 2. And of course the value of x is now 5 as appropriate. But why did it go to state 2? It's because Cameo incorrectly treats this as a choice point rather than junction. That is, the Cameo simulation toolkit incorrectly implements the UML and SysML standard for execution of actions and junctions. So let's look at another example of why you might care. So let's go off to Cameo. I've got another diagram. I have to find it. Here we go. In this case, stop the execution. We have a little state machine here. We're waiting to launch. We have combat ID set to friend. It's a enumerated type. That's how Cameo rolls with strings for these. If we get a target detected, we call an operation. To call an operation in Cameo, you have to use an action language helper function, call operation, to launch. And then if combat ID is hostile, we go to guiding the missile. Otherwise, it's suspect, we do a flyby. That's how this works. However, if combat ID is friend at this point, what should happen? What should happen is it should throw this event away because all of the guards are false. No exit action, no transition actions, we don't end up in subsequent state. What does Cameo actually do in this case? Well, let's see. So let's do a simulation. So we're waiting for launch, and now we'll do the target detected event. Now notice that the combat ID has the value, as we see here, friend. So none of the guards are true. You see by the red highlight, we're currently at the junction. We're stuck in the junction. We can't exit. Even if I go and change the value of combat ID to, say, hostile, we're still stuck. This is said to be an ill-formed model. And this is why I recommend you never use choice points, because it's easy to get stuck. If you're using choice points, I recommend you always have at least one guard be else, because otherwise you'll be stuck and your model will be broken. So that's why I recommend you don't use choice points. But Cameo incorrectly implements Junction as a choice point. Now, speaking of choice points, I recommend you don't use them. But if you want to use them, Rhapsody doesn't support choice points at all in conflict with the standard. Cameo, however, does allow choice points. In this case, the choice point semantic is exactly right. You would end up in state 2 because the actions are executed first, and then when you get to the choice point, the guards are evaluated. And then we take the true path, because at this point then, because x has a value 5, we take this path to state 2. Let's talk about forks and joins. So forks allow you to bypass multiple defaults when you're going into a set of AND states owned by a composite state. Normally, if you take a transition to a composite state, there's a default for each one of the AND state regions it might own, and you go to that default. But what if you want to bypass that default? You can use a fork. Join is on the other side of that. If you have a transition exiting a composite state, regardless of what combination of nested states, it'll exit that composite state. What if you only want to take a transition if some set of different states, each in a different end state, is true, these predecessor states? Then you can use a join for that. Forks and joins are supported and properly work in Rhapsody. So in Cameo, while you can draw them, they don't actually execute. Let's take a look at that. So here's an example using forks and joins. So we've got this state machine, and if I go from state A to state B with a transition E1, I'll go to state B1 in this end state region and state B3 in this end state region, because those are the defaults. But what if I get an E2 event, I want to bypass those and go directly to B2 and B4? That's what a fork does. So it allows me to enter into non-default nested states in different AND states of a composite. Similarly, if I'm in state B, regardless of what combination of nested states I'm in, this object can transition to state C with event E4. But what if I only want to take a transition, in this case triggered by E5, if B2 is true and B4 is true? That's where I need a join. Let's watch this execute. So let's go ahead and start this up. Let's run this. State A, and just to show you, I can insert an event E1, and I'll take this transition, go to B1 and B3. Let's show you that. In fact, there we are. And then I can take the transition E4 to C. And that works as we expect. Let's go ahead and rerun this. And this time we'll take the event E2. Now notice that we bypassed those defaults and went directly into state B2 and B4. Now, event E4 will still work because regardless of what combination of nested states there are, E4 will work. But E5 will only take a transition if both B2 and B4 are true. So I take the transition B5 and we correctly transitioned to state C. Let's look at this in Cameo. Here is the same model in Cameo. Exactly the same. Fork and join. It's the same model. And let's run this. And what we see is terminates the behavior because forks and joins are not supported. I think that's a pretty glaring omission on the part of the simulation toolkit for Cameo. In addition, forks are properly implemented in Rhapsody activity diagrams as well. When you transition from an action to a set of actions because of outgoing control flows, remember that when an action completes in UML or SysML activities, it puts a control token on all of the outgoing flows. So in fact, we see after E6 completes, it puts a control token, here we see the number of tokens being put, and activates all of these actions. These properly activate in Rhapsody. You can tell by the magenta color, these are executing when I took the snapshot. In Cameo, however, it incorrectly implements the fork, even though it does support it in execution. Here we've got the same model done in Cameo, but because there's an event except action, it actually pauses and stops here, waiting for event EV2 to occur. It has not executed this action or this action. It's executing them sequentially rather than concurrently, which is incorrect. If instead you got a fork here, then it will correctly execute. All three of these actions are executing. Here you see the red circle showing where we're paused on both of these at the same time. But this only works when you have a fork in place, even though this should work as well. It does not correctly execute in Cameo. It's another defect in the Cameo simulation toolkit. Now let's talk about history. History allows you to re-enter to the same nested state when you exit a composite state. Here's a simple example where we have history. This says that whether you're in state A or state B, if you exit out to state 3 and come back in, go to the last active state. If you didn't have history, you go back to the default state, which in this case would be state A. The reason why you have a default connector to the history and history to a state is because before you've ever been in state 0, there is no history. You have to define the default in that case. Default would be state A. If there's no history, the default is state A. If you're in state B and you exit state 0 to state 3 and then come back in, you go back to state A. With history, however, if you're in state B, when you exit, you'll come back to state B. But this is known as shallow history. It only remembers the next level down in terms of history, not deeper levels. Let's run this and see how this works. So, magenta again indicates the currently active state. We're in state 0 for this object, which means the default is state A, and inside state A there's state A1. Now if I transition to B by going to state B here, and then I do a pause, now I'm currently in state 3, and I resume, it goes back to state B, exactly as I would expect. If I go back to state A, and I go to state A2, the behavior will be slightly different. I'll go back to state A, but I will go back to the default, because this is the shallow history. So let's do that. Let's go to pause. Notice currently in state A2. Pause, and resume. Went back to state A1. There's also a form of history known as deep history. Deep history is shown with a star next to the history word, the H letter, in the history connector. Let's run this. It's exactly the same form as we had before. Now if I go to state B and do pause and resume, I go back to state B. So far so good. Now if I'm in state A2, however, because I have deep history, I remember through multiple levels of abstraction what the last state is. So let's go to state A2. In this case, because I have deep history, I expect to come back to state A2. So let's pause and resume, and we see we're back to state A2. So deep history remembers through all levels of abstraction, where shallow history has only one level of abstraction that it remembers. You can send events on a state machine. You can send events from one state machine to itself, or a state machine to another state machine. In Rhapsody, you can do this by adding a send signal action, send event action, on the state machine. In this case, since we haven't specified another destination for it to go, it'll be sent here and then consumed here in a different state machine execution step. In Cameo, however, you can't put a send action on a state machine directly. You can have a behavior, either a transition effect or entry action or exit action, that invokes a behavior that sends a signal, but you cannot directly send the signal on the state machine. So the same state machine as before, shown in Cameo, has this entry action on state A3, invoking a behavior called ePropagated, which is an activity which sends that event. This works the same, but there is some additional effort when you want to send signals on a state machine in Cameo versus how you can do it in Rhapsody. So let's summarize what we've seen. We talked about defaults, terminal, pseudostates, and the diagram connectors, which is a Rhapsody only thing. We talked about junctions and how both Rhapsody and Cameo deviate from the standard in different ways. Conditionals, which is a Rhapsody only thing, makes up for the problem that Rhapsody has with junctions. It's not supported in Cameo. Cameo, however, implements junctions as if they're choice points incorrectly. Choice points are supported in Cameo, but they're not supported in Rhapsody, and they are supported in Cameo correctly. Although, as I mentioned, I recommend you don't use them. We talked about forks and joins, and how Rhapsody correctly implements forks and joins for bypassing default nested states, going in with a fork and exiting with a join. You can draw them in Cameo, but they don't execute at all. Exit and entry points we'll talk about in the next episode, having to do with submachines, so we skipped over that. We talked about shallow and deep history, how shallow history remembers within a composite state what is the last active state and returns there. Shallow history remembers only one level deep, and deep history remembers through all levels of abstraction and nesting. We talked about send actions, how, even though this is an action on a pseudostate, how you can do directly on a state machine in Rhapsody. In Cameo, you have to build another behavior, typically an activity, to send the action. So you require at least another diagram to do so. So that's a brief look into pseudostate semantics in Rhapsody and Cameo and UML and SysML. We will discuss entry and exit points in the next episode. If you like this video, please click subscribe. If you want to be notified when additional videos are inserted into the channel, click on subscribe. If you want to know more about UML, SysML, model-based system engineering, or model-driven development, please visit my website, www.bruce-douglas.com. Thank you very much.